Welcome back to Anton Math. Now, in the last couple of videos, we've talked about binary relations, compound relations to create new binary relations, and inverse relations, which are themselves, again, binary relations. But in this video, I wanted to just do an example that encompassed everything we're talking about, so we can get some hands-on experience and feel a little bit more comfortable with what all of these mean. So let's suppose that I have these sets R, S, and T, where R is 1, 2, S is 3, 4, 5, and T is 6, 7. And I have these binary relations, tau from R to S, rho from S to T, and sigma, which is also from S to T. And these relations are defined by these ordered pairs here, right? So these are the elements that satisfy these relations from the respective sets. And I want to look in this example at a couple of our compound relations using these binary relations as starter points, as well as some inverse relations. So let's start off with some composition. Let's look at rho composed with tau. Now this is going to be all of the ordered pairs where tau is satisfied from R to S, and with that same S, rho is satisfied from S to T. So I'm going to be looking at all these ordered pairs in tau where the second element is the same as one of the first elements in rho. Right? I'm going from 1 to 3 with tau, and then in rho I'm going from 3 to 6. So tau, or rho composed with tau, is going to take me from 1 to 6. Now I also have a 3, 7 in rho, so I'm going to have a 1, 7 with the same first ordered pair for my tau. And let's see if we have anything else. Do I have any other ordered pairs here where the second element is the same as the first element in rho? And I do. I have this one right here, don't I? I have 2, 5, and 5, 7. So rho composed with tau has the ordered pair 2, 7. Okay, let's do another composition, get a little more comfortable. I can look at sigma composed with tau, right? Tau is going from R to S, sigma is going from S to T, so I can look at this composition. So here I'm looking at the sets RS, or the ordered pairs RS and tau, where that S corresponds to one of the S's in the ordered pair ST in sigma. So I have 1, 3 corresponds with my 3, 6, right? I have the same S in both of them, so I'm going to have a 1, 6. I don't have any more 3's here, so let's look at the second one. I have 2, 4 is going to correspond with both 4, 6 and 4, 7, isn't it? So I'm going to have 2, 6 and 2, 7. Now 2, 5 doesn't correspond with anything because S equals 5 doesn't appear as the first component of any of these ordered pairs. So this is my entire composition. Now what if I wanted to look at something like sigma composed with rho? Now here I'm going to write not defined. Because what sigma composed with rho means, right, remember that both sigma and rho are going from S to T, that means that I have some pair, ST, that satisfies rho, and then that T satisfies sigma for some other T. But that doesn't make any sense because sigma is from S to T, not from T to T. Right? So this is not defined. This would only be defined if S and T were the exact same set. All right, well, let's look at some of our unions and intersections now. If I have rho intersected with sigma, right, I can intersect these because they're going to and from the same sets, S and T. So this is going to be all of the ordered pairs that satisfy rho and satisfy sigma. And we see, looking at here, that's only going to be 3, 6, right? So this set notation is useful because when we look at intersections and unions, I can treat them just like intersections and unions of the respective sets that those relations represent, right? This is just the intersection of these two sets, rho and sigma. Now rho union sigma, it's going to be a little more generous. This is going to be all of the ordered pairs that satisfy either rho or sigma. Now we don't need repetition when we write a set, right? So this is just going to be 3, 6. 3, 7, 4, 6, 4, 7, and 5, 7. Right, I've reorganized it a little bit. But these are all of the elements that are in rho or are in sigma. That's exactly what our union is here. Now when we talk about an inverse, let's say I want to look at tau inverse. We know that if we have a relationship tau, the inverse is going to be all of the ordered pairs where the role is changing between R and S, right? These are all little r followed by little s's. My inverse is going to have the same ordered pairs, but with the little s's first and the little r's following. So in other words, I'm just going to switch the order of all the ordered pairs. That's all we need to do here to find the inverse. So it's going to be 3, 1, 4, 2, and 5, 2. And of course, we can take the inverse of any of our compound functions, or compound relations, sorry. Let's say I want to look at the inverse of rho composed with t, the first one we did. So this is rho composed with tau inverse. Again, I can just switch the roles of all the elements in these ordered pairs. So this is going to be 6, 1, 7, 1, and 7, 2. Now remember, this is also going to be equal to tau inverse, tau, not t, tau inverse composed with rho inverse. So if we wrote out what rho inverse was and composed them in this way, we would get the exact same thing here. Okay. So I hope that kind of clears up some of these compound relations that we've been doing. In the next video, I'm going to talk about some properties of relations that are to and from the same set, and then we'll be moving on to some special relations in the next section. We'll see you there.